Section 7.4, sum to product and product to sum formulas. In this section, we're going to take a look at two families of identities that allow us to write the product of two trig functions to the sum of trig functions, or the sum of trig functions into a product of trig functions. First, we'll look at the product to sum identities. We have four product to sum identities based off of how we're multiplying cosine of an angle and sine of an angle. First, cosine of alpha times cosine beta equals 1/2 cosine of alpha minus beta plus cosine of alpha plus beta. To verify that this identity is true, we're going to start by simplifying the right-hand side, which we can use the sum formulas for cosine that we learned in the previous section. Cosine of alpha minus beta becomes cosine alpha cosine beta plus sine alpha sine beta, while cosine of alpha plus beta becomes cosine alpha cosine beta minus sine alpha sine beta. The sine alphas and sine betas cancel. We can add our cosine alpha cosine betas together, and they'll combine to 2 cosine alpha cosine beta, or the 2's will cancel. And you see we get the right-hand side. The other three identities on the slide can be proven in a similar fashion. The other three are sine alpha sine beta equals 1/2 of cosine alpha minus cosine beta minus cosine of alpha plus beta. Sine alpha cosine beta equals 1/2 sine alpha plus beta plus sine alpha minus beta. Cosine of sine beta equals 1/2 of sine alpha plus beta minus sine of alpha minus beta. As an exercise, try verifying the other three product to sum identities at home. In these exercises, we're going to practice with the product to sum identities to write each product as a sum. An exercise like this is pretty useful in calculus, especially for certain operations where we would prefer to work with addition over multiplication. So looking at the first example, we're going to leave that 6 off to the side, and we're primarily going to be focusing on the cosine 8x sine 3x. If we apply the fourth product sum identity on our formula sheet, we have 1/2 times sine of 8x plus 3x minus sine of 8x minus 3x. We can multiply the 6 and the 1/2 together to get 3. 8x plus 3x is 11x. 8x minus 3x is 5x. And then we can distribute into 3 to drop the parentheses. And we obtain 3 times sine 11x minus 3 sine of 5x. Now, even though we have subtraction, all subtraction is addition with a negative. So we have written our product as a sum. Next, 22 sine 44y times sine 22y. Here, we're going to apply the second product to sum formula. We'll leave the 22 off to the side and focus on the sine 4y, sine 2y. That will become 1/2 times cosine of 4y minus 2y minus cosine of 4y plus 2y. 22 times 1/2 is 11. 4y minus 2y is 2y. 4y plus 2y is 6y. And then we can distribute in the 11. We get that 22 sine 4y times sine 2y equals 11 cosine 2y minus 11 cosine 6y. Now we're going to find the exact value of the following expressions. First, sine of 5 pi over 24 times cosine pi over 24. Notice that 5 pi over 24 and pi over 24 are not located on the unit circle. But since we're multiplying two trigonometric functions together, we can apply our product to sum formula in order to rewrite our expression. According to the third product to sum formula, this will equal 1/2 of sine 5 pi over 24 plus pi over 24 plus sine of 5 pi over 24 minus pi over 24. Now we can simplify each input, and we get 1/2 of sine pi over 4 plus sine pi over 6. Both angles are located on the unit circle, so we can find the exact value. Sine pi over 4 is √2 over 2. Sine pi over 6 is 1/2. Add what's inside of the parentheses, and we have 1 plus √2 over 2 multiplied by 1/2, and we have 1 plus √2 over 4. So sine 5 pi over 24 times cosine pi over 24 equals 1 plus √2 over 4. Next, we're going to find the exact value of cosine 285 degrees times cosine 165 degrees. Just like in the previous example, 285 and 165 do not appear on the unit circle. So we'll try to use the product to sum to see if we can find the exact value. Using the first product to sum formula, after applying the product to sum identity, we get 1/2 cosine of 285 minus 165 plus cosine of 285 plus 165. After applying the product to sum identities, we have 1/2 cosine of 285 minus 165 plus cosine of 285 plus 165, which simplifies to 1/2 cosine of 120 degrees plus cosine of 450 degrees. Going to our unit circle, cosine of 120 degrees is negative 1/2. 450 degrees is coterminal to 90 degrees, and cosine of 90 degrees is 0. Now, when we do negative 1/2 plus 0 times 1/2, we get that the exact value of cosine 285 degrees times cosine 165 degrees is negative 1/4. The next set of identities can be very helpful when we're trying to solve equations. These identities are the sum to product identities. The first sum to product identities is sine of alpha plus beta equals 2 sine of alpha plus beta all over 2 times cosine of alpha minus beta all over 2. These properties can be derived from the product to sum identities. If we start with the left-hand side of the first identity, we can apply the third product to sum identity, similar to what we did in example 1, and we get 2 times 1/2 sine of alpha plus beta over 2 plus alpha minus beta over 2 plus sine of alpha plus beta over 2 minus alpha minus beta over 2. Now we can simplify. The 2's and the 1/2 outside cancel. When we add alpha plus beta over 2 with alpha minus beta over 2, our denominators are already common, and we can see that the betas would cancel, leaving us with 2 alpha over 2 in the first sign. And in the second sign, the alphas will cancel, and beta minus negative beta will be 2 beta. Now we can cancel out the 2's, and we're left with sine alpha plus sine beta, which is the left-hand side of our identity. Through a similar process, we can verify the other 3 sum of the product identities. Those are sine alpha minus sine beta equals 2 sine of alpha minus beta over 2 times cosine of alpha plus beta over 2. Cosine of alpha plus cosine of beta equals 2 cosine of alpha plus beta over 2 times cosine of alpha minus beta over 2. And lastly, cosine alpha minus cosine beta equals negative 2 sine alpha plus beta over 2 sine alpha minus beta over 2. Next, we're going to write the sum as a product. The reason why we would want to be able to write a sum as a product is, let's say we were trying to solve for t, and t was set equal to 0. With t being set equal to 0, by writing as a product, we could utilize the zero factor principle and then set each factor equal to 0. We will talk more about trigonometric equations later, but for right now, let's just practice simplifying them. Since we're subtracting cosines, we can apply the last sum of the product identity, and we get that our expression equals negative 2 sine of 6.7t plus 2.4t all over 2 times sine of 6.4t minus 2.4t all over 2. If we simplify each expression inside of the sign, we get negative 2 times sine of 9.1t over 2 times sine of 4.3t all over 2, which simplifies to negative 2 sine of 4.55t times sine of 2.15t. Next, we'll write sine of 15t plus sine of 13t as a product. Since we're adding sines, we'll apply the first sum of the product identity. We get 2 sine of 15t plus 13t over 2 times sine of 15 minus 13t over 2. Simplify the expressions inside of the sign, and we get that sine 15t plus sine 13t is 2 times sine 9t times sine t. Next, we're going to find the exact value of the following. First, cosine of 15 degrees plus cosine of 75 degrees. Now, there are a couple of different options we could take now because of how many identities we have. But with this one, let's use the sum to product to see if that helps us evaluate this a little quicker. Since we're adding cosines together, we'll use the third sum to product identity. And we get 2 cosine of 15 degrees plus 75 degrees over 2 times cosine of 15 degrees minus 75 degrees all over 2. Then we can simplify. 15 plus 75 is 90, divided by 2 is 45 degrees. 15 minus 75 is negative 60. Negative 60 divided by 2 is negative 30 degrees. Now we can evaluate each separately. Cosine 45 degrees is root 2 over 2. As for the cosine negative 30 degrees, you can either find the coterminal angles or use the even-odd properties. Since cosine is an odd function, the sign doesn't matter. So cosine of negative 30 degrees is the same as cosine of positive 30 degrees. Cosine of positive 30 degrees is root 3 over 2. The 2 outside here will cancel out with one of the 2's in the denominators. And when we multiply, root 2 times root 3 is root 6. So we get that cosine of 15 degrees plus cosine of 75 degrees is root 6 over 2. Next, we're going to find the exact value of sine 17 pi over 12 minus sine 13 pi over 12. Neither 17 pi over 12 or 13 pi over 12 appear on the unit circle. Now we could go ahead and use the double angle formulas to evaluate each one individually. Let's see what happens when we apply the sum to product rules. Since we're subtracting sines, we'll apply the second rule, and we get 2 sine 17 pi over 12 minus 13 pi over 12 all over 2 times sine of 17 pi over 12 plus 13 pi over 12 all over 2. And when we subtract and add our angles, we get pi over 3 and 5 pi over 2 respectively. Divide each angle by 2, and we get that our difference is equal to 2 sine pi over 6 times sine 5 pi over 4. Now we can turn to our unit circle. Sine pi over 6 is 1/2. Sine of 5 pi over 4 is negative root 2 over 2. And when we simplify, we get negative root 2 over 2. Next, we're going to simplify the following expression. Sine of 7x plus sine of 5x all over cosine of 7x minus cosine of 5x. Taking a look, notice how we're adding and subtracting cosines in the numerator and denominator respectively. If we can rewrite these sums as a product, perhaps we would be able to use quotient identities, or perhaps we might be able to cancel out common factors. If we apply the first sum to product formula to the numerator, we get 2 sine of 7x plus 5x over 2 times cosine 7x minus 5x over 2. If we apply the fourth sum to product formula to the denominator, we get negative 2 sine of 7x plus 5x all over 2 times sine of 7x minus 5x all over 2. Now, before we simplify the inputs, notice that we have 2's as a common factor in the numerator and denominator, so they'll cancel. And sine of 7x plus 5x over 2 is a common factor in the numerator and denominator. So we can cancel those out and not have to worry about simplifying. Now, we still have the negative in the denominator. We can bring that off to the side, and we can evaluate the 7x minus 5x over 2 in both of our trig functions. And when we do, we get negative cosine x over sine x. Using the quotient identity, cosine x over sine x equals cotangent x. So our expression simplifies to negative cotangent of x.